Yeah. Hello, everyone. I'm Alex. So, as I'm speaking, if you've got any questions or anything that looks wrong, then feel free to shout out, and I will answer appropriately. Okay. So yeah, I'm going to be talking about what I've called the spaces between, which is basically about trying to reason about fault-tolerant space-time volumes under code deformations. So there's been quite a lot of work on doing surgery with LDPC codes in the last couple of years. I think we're kind of reaching the point where, rather than just reasoning about doing a particular logical measurement or set of logical measurements in one kind of logical round, we now want to think about the kinds of macroscopic space-time structures and volumes that one acquires by doing these kinds of deformations. For simplicity and my own peace of mind, I'm going to only consider the phenomenological noise model, and I'm only going to consider CSS LDPC codes. And I'm also, as an addendum to that, I'm also going to only consider surgeries which maintain the CSS property. So I'm not going to be measuring Y's or Z tensor X or anything like that. And the fact that I care about the phenomenological noise model and LDPC codes is kind of partially justified by the fact that I'm going to live in my happy land of only caring really about asymptotics, because if I have an LDPC code, then the hook errors that I can get are bounded in weight, and so if you kind of combine phenomenological noise with LDPC-ness, then up to some constant, which might be hugely, vitally, practically important, but not asymptotically important, I can kind of reason about circuit distance as well, kind of on the low. Okay, so this talk that I'm going to give is based on, well, actually it's based on the appendix of a paper from October, which was joint work with some very nice collaborators, Sunny, Dom, and Ted Yoder. Okay, so I think I'll probably breeze fairly quickly through this kind of stuff. But if we're doing lattice surgery with plain old surface codes, then we initialize some new qubits and some new checks, and we deform some old checks as well. And then we measure for some number of rounds, and the product of these new stabilizers which we've introduced will determine the logical measurement outcomes of some logical qubits in the code. And then after we are done with our ancilla system, we're going to measure it back out again. And actually something which I did want to bring up, which I think people quite often gloss over, pardon me, is that after you measure out, you have this kind of frame error that you introduce on your original code, because once you measure out, you're going to have some stabilizers which don't commute with the stabilizers which you introduced in the surgery procedure. But this is fine, because when you measure out the ancilla qubits in the middle, you can take the products of those with the stabilizers that you have afterwards, and so you still know deterministically what their outcomes should be up to some fault distance. Okay, so with plain old lattice surgery, it's very easy to prove the phenomenological fault tolerance of doing a single surgery operation, at least with kind of what we know now. And realistically, when people think about doing lattice surgery with surface codes, they don't really talk so much about doing individual operations anymore. People talk about doing kind of space-time volume optimizations and compilation and so on. And this is happily very nice and kind of elegant, because one can associate a particular surface code patch that is being measured for D rounds with a kind of voxel, where we have some like smooth boundary and rough boundary here. And then you have this kind of nice kind of space-time sort of ambivalence, and you can construct things like a C0 made by I guess you could think of this as being an XX measurement and then a ZZ measurement, although there are other kind of equivalent ways of thinking about it as well. And this is actually very nice, because you can inspect the fault distance of your overall space-time volume that you're reasoning about by inspecting the pipes and making sure that their widths are the appropriate size and that you don't have any kind of non-contractible closed curves that are very small. And so you can kind of reason about them kind of nicely and topologically, even though doing kind of optimal compilation to try and compress the size of these things is NP hard, and people use like SAT solvers and stuff, or Craig Gidney. If we're wanting to think about the space-time volumes of LDPC codes as well, and surgeries upon these things, we're kind of inevitably going to lose this nice topological parallel, and instead we're going to have to replace it with some homology instead. Or at least that's how I'm going to do it. Maybe there are other ways. Okay, so it's very well known that if we have a CSS code, then we can describe it as a chain complex with three terms in it. And importantly, each of these vector spaces is equipped with a basis such that you can really think of these vector spaces as being F2 linearized sets on kind of the basis elements of these things. And you can read off the parameters of your code from various kind of homological properties. In particular, the quantum dimension of the code is equal to the dimension of the homology space at degree 1. Okay. This is also like fairly standard. I'm not doing anything new yet. So if you want to perform some kind of Z-logical measurement by surgery, there are a few different formalisms for this, but quite a convenient one is in terms of mapping cones. What we're going to do is we're going to start off with our initial CSS code here. And we're going to introduce some kind of ancilla complex up here, which has to have a chain map which commutes, so going down and across is equal to going across and then down. And we don't actually ever make A and C as being separate things in our procedure. Instead, what we do is we go straight from C, our original code, to the mapping cone of F. And this is, whereas the top thing is a map, this is a morphism, the bottom thing is a kind of bona fide chain complex. So this describes a code. And the idea is that we've just shunted the degrees of our ancilla complex along by 1, and then we've introduced some direct sums to kind of take the total complex of this thing. And this is still going to commute as a chain complex by virtue of the fact that if you go down and across, then it's the same as going across and then down. And the same thing happens when you shunt everything along. So to kind of maybe give some intuition for this, if we have two surface code patches, which are distance 2, then if I take some vertex and 2 edges here, then this is going to be my A complex. And my map, F, is going to map both to the left direction from this vertex and to the right direction from this vertex, and the same for edges. You can check that this is coherent and all that. And then when I do take my mapping cone, then I shunt the degrees along by 1. So what was previously a vertex before is now an edge, and the chain map is now part of the differential of the coned code. And then I haven't drawn in visually the faces, but the 2 edges have now become faces. Okay, and the point of doing this is all primarily to preserve kind of sparsity while being able to measure the logical operators which you would like to measure. So if you want to, you can make some kind of fairly fancy ancilla complex. And if you want to compute kind of what the logicals you've measured are and whether you've incidentally introduced any new ones and this kind of thing, then you can construct a short exact sequence. So to give some intuition for this, if you forget entirely about the differentials and just look at the mapping cone which I had here, then you can see that this is a direct sum of 2 vector spaces at the bottom. And so I can always build a short exact sequence from the splitting of these 2 vector spaces. And then if I add in the differentials back in, then I claim that this gives you a map between this short exact sequence of chain complexes. And then I can do a snake lemma, which essentially turns this short exact sequence into a long exact sequence on homologies. Okay, you might be thinking like, well, this is kind of way too gritty stuff. But well, I'm going to do some more grit, but then I'm going to like try and kind of explain why this maps to things that people have done before. Okay. So in particular, if you have this long exact sequence, then you can use rank nullity and similar kind of standard linear algebraic tools to work out what the dimension of the quantum dimension of my coned code is going to be. And if you make a very minor assumption, which is very easy to satisfy in practice, then you can get down to something which looks like this at the bottom, where I have some homologies of my different chain complexes, and then also I have to include some kind of rank of a matrix here. So if I kind of go back out and look at what Isha was talking about in her very nice talk earlier, then if I choose my A to be a graph, let's say a graph complex, where I associate my A1 with V, my A0 with E, and my A-1 with a set of faces or cycles F, then if I translate what I was saying before with this expression into this language about kind of graphs and doing kind of gauging logical measurement, then the number of logical qubits I'm going to have is going to be determined by the number of original logical qubits I had in my code, the number of measured logicals, that is the ones that are turned into stabilizers and therefore they're gone. And then Isha talked quite a lot about how it's very important to gauge out the cycles in your graph by adding faces. And the reason for this is because these can add new elements to your homology space and therefore add new logical qubits. And you also have a term on the other end, because sometimes, broadly by coincidence, some of these faces or cycles happen to be stabilizers anyway of the cone code. So this is kind of like how you can portion up kind of the thing that Isha was saying into something a little bit more algebraic. And so in particular, the thing that Isha was saying about making an expander graph with that's been decongested to have all of its cycles gauge fixed is basically saying that we don't want to bother with these kinds of annoying this dimension here and this dimension here. These are a pain to handle, and so we want to make sure that our ancillar complex A is exact at degree 0, which means that we eliminate those terms. Okay. Now the other thing that you have about choosing a graph complex is that, assuming that the graph is simply connected, and there's some good reasons for assuming that, then the dimension of this homology space is going to be 1. And so the maximum number of logical qubits that you can measure simultaneously with a single one of these graph complexes at the same time is going to be 1. So I'm going to kind of breeze through stuff about code distance. So first of all, assuming that we're doing a Z logical measurement and our A complex is exact at degree 0, then the X distance of our cone code is always going to be at least D. The Z distance is a bit more complicated and requires a cleaning argument. And I think Isha actually gave a pretty good description of this. But in terms of the chain complexes here, the idea is that because there are no new logical qubits, all of the logical representatives must be stabilizer equivalent to logical representatives which existed in our previous code. And so what we need to do is check that none of the logical representatives that are wholly contained in here, which must have weight at least D, can be cleaned by multiplying them by new Z checks into something which has weight lower than D elsewhere in the ancilla code. And there are a whole bunch of ways of trying to give conditions such that this is satisfied. So in particular, if you have graphs, then you can think about sort of normal Cheeger constant type stuff, or generalizations of this, which Isha was talking about as well. There are a whole bunch of kind of more recent works, some of which are talking about surgery and some of which are talking about kind of more general quantum embeddings of codes. But all of them kind of morally are saying the same thing, which is that you want to have some kind of isoparametric inequality such that you're always going to spit out support on your ancilla complex, which is at least as much as whatever support you've cleaned off. That's actually technically slightly inaccurate, but that's kind of morally what's going on here. Okay, so my vibes-based summary of the ingredients that you want in order to make this kind of coned code have good code distance is you want this exactness, so you don't introduce any new nefarious logical qubits. You want some kind of expansion at degree 1 so that you can clean safely. And you want your chain map to be sufficiently sparse. This is partly because you want to preserve the LDPC property, because otherwise there's no point in doing LDPC surgery at all. And partly because if this is a more dense matrix here, then you could end up cleaning more support off here with each particular element. Okay, and for graph complexes, happily satisfying these conditions is nice and easy because there are efficient randomized constructions of expander graphs, and there are many ways of, like decongestion lemma and similar ways of modifying it slightly so that you can gauge out all the cycles and you don't introduce any new logical qubits. However, if we want to do something that's more parallel, or we want to do some kind of single shot surgery or anything of that nature, then we really need our A to be something other than a simply connected graph, because it can only measure one logical at a time. And constructing good ancilla systems is, at least asymptotically, is really, really hard. And it's kind of connected to the fact that it's hard to construct systolic expanders as opposed to expander graphs. Okay, so this is all a bit of like fancy schmancy asymptotic stuff. In reality, as Isha said, in practice what people normally do is they make some ancilla system that's kind of an ansatz, and then if they find that it doesn't preserve the code distance, then they just add extra stuff into that ancilla system such that you're going to satisfy this kind of expansion type property to a degree sufficient to preserve the code distance. I want to comment on this slightly because really when you're, okay, so distance is like a useful kind of figure of merit, but really what you care about when you're making some fault-tolerant logical protocol is you care a lot about the weight enumerator of your code, either a space-time code or a literal code. And this, I think, is one of the reasons why these bivariate bicycle codes work quite well, is because even though the distance might be, some amount, a lot of the logical faults that you can get are actually quite a bit higher weight than that. And if you don't make something that's expanding here, if you just kind of do enough to preserve the code distance, then even though you're not going to clean to have something that's lower weight than D, you could end up with a whole bunch more representatives which are much closer to weight D. And so the logical error rate against stochastic noise is going to be a bit worse. There's also another problem, which I'll get to later, with doing this kind of like ad hoc constructions of ancilla systems. Okay, so there's a kind of a very general result, which is from Dom and Ted, which more or less says that if we have that the code distance of our coned code is at least D, then we can guarantee that if we, assuming we're doing a Z measurement, if we initialize the new qubits in plus and then measure all the stabilizers for D rounds and then measure out those new qubits afterwards, then this is a process with phenomenological fault distance D, but there's kind of a caveat here, which is that basically, as with the study of most fault-tolerant protocols, one either kind of assumes perfect syndrome rounds before and after to ensure that time-like errors from elsewhere, which you don't know anything about because you're just studying that single protocol, can't enter, or kind of equivalently D rounds of measurement in general, unless the code is single shot in some way, where these D rounds of measurement are also present to ensure that time-like errors can't kind of enter into your protocol from elsewhere and cause problems. So yeah, you could rephrase this in terms of code space preparation, because when you're deforming these codes kind of out and back, it's kind of very similar to state prep, really, because you're getting this kind of frame error and all of this kind of jazz. So this doesn't really change the asymptotics if each surgery takes D rounds, because if each surgery is taking D rounds and you wait for D rounds between each one, then you're only increasing the time by a factor of 2, which, okay, massive pain in real life, but for asymptotics is not such a big deal. But if you want to do surgery in fewer than D rounds, for example, if you have 4D toric codes, or which you can do in kind of square root D rounds, or you want to do something which is genuinely single shot, then this can be a big headache. And so there are a couple of papers. There's a very nice one by the Iceberg team on fast surgery, where they kind of introduce a set of meta checks. So you have another term in our auxiliary complex. I'm not really going to go into the actual constructions. Perhaps you can tell that throughout this whole thing, I'm kind of skimming over the literal details of all of the constructions, because I want to get to the point where I can talk about volumes of these things. But yeah, you introduce some meta checks with some kind of distance associated to this map here, such that you can check all of the new stabilizers that you've introduced against each other, and reduce the time overhead of your surgery without reducing the fault distance. I also want to note that if you, there are many ways of reducing kind of the time overhead of surgery which are geared towards stochastic noise, which is more realistic. Whereas because the setting that I'm talking about here is specifically phenomenological fault distance, one can't do something like a complementary gap calculation, or like a time-encoded lattice surgery or anything like that, because they kind of work on purely on stochastic noise. Okay, and actually another thing I'm going to say is that not only is this a construction of doing this kind of fast surgery or single shot surgery, but if the thing that you're concerned about is phenomenological fault distance, then this kind of meta check is actually necessary. So you can't get away with just making a coned code which has some kind of broad expansion property, like quantum Tanner codes or anything like that. The interface between the ancilla complex and the main one is such that you need meta checks in order to speed up the surgery without lowering the fault distance. Yeah, okay, so we have a very similar kind of argument as before about being able to do everything with phenomenological fault distance D, where the main difference is now that we have this kind of meta check distance, which has to be sufficiently high, and now we're measuring all of the stabilizers for order 1 rounds instead of order D. But we kind of have the same this kind of same issue down here as well, which is that this claim here kind of requires either perfect syndrome rounds or D rounds of measurement before and after, and now that is kind of asymptotically a problem, because we could construct a logical circuit composed of these surgeries, where all of my surgeries are super fast, but I'm waiting for D rounds between each one, and so asymptotically, like the amortized cost in time of all of my surgeries is still going to be D. Okay, so now what I want to talk. So this is what I meant by the spaces between, by the way. Is this kind of idling step that we have between these surgeries, which I want to get rid of. So to go further than this, I need to reason about spacetime codes. So far, everything that I've said has been like, we take a code, we take some kind of mapping cone or construction on this code to get a deformed code, and then we're just going to we're going to transition from one to the other and back and so on. But to reason about what's happening in the full volume, you really need some more kind of technology, and luckily Timo and Mike and some other people kind of provided that technology in the form of fault complexes. So a fault complex is very MBQC inspired, although it is not kind of you can also reason about other things with it. And the idea is basically that rather than having a 3-term chain complex where I have kind of qubits and x checks and z checks, I'm instead going to divvy up my my space-time fault locations into x type and z type. So evidently this kind of entails some CSS type structure on my space-time volume. And then I'm going to have z detectors, which are going to detect x kind of fault locations, and x detectors, which are going to detect z kind of fault locations. And in particular, Oh, I've got an example here, that's nice. Okay, so if you start off with a unit cell of surface code, where I've got like you can imagine there's further tanagraph beyond this, but the unit cell is kind of complicated enough. Then what I want to do is I want to reason about the space-time volume of this kind of idling. So I can think of this as kind of a voxel in the same sense as these pipe diagrams earlier. And so these crimson checks, or these crimson boxes, are going to be my X detectors. These are going to be some Z fault locations. And these are going to be X fault locations, and these are going to be Z detectors. And the idea is that, as with MBQC, pardon me, we are kind of splitting up the syndrome rounds into first kind of X type and then later Z type. And what this means is that you can construct all of the detectors kind of interleaving with one another. And so you can describe some kind of more general kind of space-time volume rather than just a single code or snapshots of a space-time volume in this way. Yeah, if anyone has any questions about this, then now's probably a good time to ask. Cool. Okay, so in particular, I'm going to assume that when I said I have kind of X fault locations, this is going to be a combination of X Pauli faults, that is faults on what you can morally consider qubits, and Z check faults. And the Z detectors are going to be composed of Z checks and some state initializations, perhaps. And so they're going to, or sorry, have I got that the wrong way around? Basically, they need to be able to detect X Pauli faults and Z check faults. And as before, I'm going to use the homology to try and study equivalence classes of various things. And in particular, if I take my chain complex at degree 2, then technically speaking, this is a superscript rather than a subscript, so I'm thinking about the chain complex going the other way to make it a co-chain complex, but that's by the by. The point is that at degree 2, I can classify equivalence classes of X-type logical faults. And the same thing for Z-type logical faults at degree 1. So now, unlike with a code, where I have both of kind of the homology space has this isomorphism between the homology space of the chain complex and the homology space of the co-chain complex. Now these live at completely different degrees, and you can kind of you can also describe space-time stabilizers using this picture, and also logical correlations as well using various maps from this. So it's a lovely construction, basically, is my point, and one can take a CSS code and then, hello?
Yeah, I have maybe a dumb question. So why is that, if you go back to the previous
Yeah, sure.
what is the map from Pauli faults to, X Pauli faults to
Oops, sorry, my bad. Please continue.
Yeah, what is the map from X Pauli faults to Z Pauli faults?
Yeah, so you can think of this map as essentially saying this is like the world line of a qubit in time. So this is saying that if I were to think of this as being like a circuit that I'm operating on qubits with rather than an MBQC graph state, then this is like, so if I go back to here, this is like saying I have, this is a fault location here, and then this is a fault location here, and then this is a fault location here, and what type it is alternates depending on which stabilizers are being measured at that particular interleaving time step. And so if you were to think of this as kind of the world line of a data qubit in a circuit, then this would be like saying that you have locations between syndrome extraction rounds where it can either experience X or Z faults.
So does that mean that the map just sends like a Z arrow to an X arrow at the same location?
It doesn't always have to do so. On the next slide, I'm going to assert that that's the case. Okay. So in particular, if I start off with any arbitrary CSS code, then I can kind of take the foliation of this, which again you could either sort of think about in terms of circuits being with syndrome extraction over time, or you could think about it in terms of a kind of cluster state. Happily, you can get this, everyone says, oh, syndrome extraction for repeated rounds is like taking the repetition code. Well, it literally is, like formally, which is maybe not surprising, but it's kind of neat, where you take your initial code, and then if you take the tensor product, then you get this kind of structure. In particular, you get this kind of, because it's a tensor product, you have this identity tensor something along the middle, and that's basically why you have this kind of one-to-one type mapping.
So, sorry, going back to the picture you had.
Yep.
Yeah, it's like I feel like I'm getting confused between the edges and the vertices. So like the Z how default would be like the edges.
No, so every vertex is so you can think of this as just like an incidence complex. So the edges determine the incidence of the matrices, but there's no sort of basis elements living on edges. All the basis elements live on vertices.
Right.
Yeah.
So if, for example, I have a if I look at like one of those like blue, yellow, blue
Yeah.
lines, and I take like I imagine that one of them is like X and the other is Z.
Mm-hmm.
So like, say that I pick the Z one, what does the map give me?
So the map will the map will be the repetition code map tensored or the map specifically along this line anyway, because you also have other maps in the chain complex, but the map specifically along this line will give you the repetition code matrix tensored with identity.
Okay. So for example, the yellow dot would give me like both blue dots above.
Yeah, and then the other map in the if I go here, the other map here is doing the horizontal, is connecting it to the horizontal things as well.
And is that like is that a straightforward way to like think about this like LDPC formalism in a circuit based way?
That's normally how I try to picture it. I think technically there's some subtlety because it hasn't actually been proved that if you take a fault complex and then rewrite it as a circuit, then the phenomenological fault distances transfer between the two. But it seems like one of those things that's like immediately obvious, which makes me worried it might be wrong. But like it seems pretty concrete to me. Okay. There is another complication which I'm just going to largely ignore unless there's time at the end, which is basically that because you're making a kind of graph state and then you measure out all of the qubits in the graph state at the end, this complex that I'm describing actually only defines a scalar if you think about it in terms of circuits, which means that if you want to reason about fault-tolerant protocols, then this is a bit tricky because by definition you can't have time-like errors entering or leaving. But we basically hacked around that by introducing a bunch of checks at the bottom and top of the space-time volume which can have errors on them, so that you can introduce wild lines through the volume. And our justification for that was like, look, it works. So I hope that's satisfactory. Okay, so now if we take a surface code to begin with and then do this tensor product with the repetition code, then we can make one of the logical blocks which appear in those kind of pipe-like diagrams, where you can imagine rough boundaries and smooth boundaries. But now what we want to do is we want to reason about space-time protocols. So I'm not concerned with just idling states of codes. I want to reason about doing a bunch of surgeries on these, and in particular, like more than one, and ideally as many as I want. So in this case, earlier I had like, oh, you define your deformed code by taking your initial code and then taking a mapping cone on this, and then this gives you your deformed code. So now what I'm saying is that in order to construct the space-time volume for these kind of deformed codes, I'm going to take the mapping cone on the space-time volumes directly rather than on the kind of individual codes. So first of all, what I'm going to do is I'm going to take whatever ancilla complex I had, and I'm going to tensor it with another repetition code. Its repetition code's all the way down, I'm afraid. And technically this is the dual of a repetition code, but that's just to do with whether you're doing a z-basis measurement or an x-basis measurement. And so what this is basically saying is that if my alpha parameter is determining what the block length is of my repetition code, this is saying how many rounds I'm measuring my surgery protocol for. So this could be D, it could be less than D. And then what we're going to do is we're going to take this whole thing, which could include meta checks as well, which are the A2 components here. And then we're going to do a mapping cone with a map from this into our big fault complex for the idling volume. And in particular, if this alpha is kind of D-ish, then whatever repetition code we took our initial code with to do the idling volume, we want to be much bigger than D, so that we can glue in many of these mapping cones at different time-like steps. Hello? Yep.
So previously you showed where you took the chain complex associated with CSS code,
Yeah.
tensor data into the repetition code, and you took the cone of that.
Mm-hmm.
Is that now hiding in this like P of alpha?
Yeah, totally. So if you were to take kind of like if you were to take kind of a slice through the resultant thing of taking the cone of this is just the chain map. I haven't actually shunted all the degrees yet. But if you were to take like a slice through this, then yeah, you'd get exactly one of the codes or deformed codes that I was constructing earlier. Okay. So, all right, I've done a bunch of stuff. Why am I doing all this stuff? One thing that's kind of neat, which doesn't justify this research in and of itself, but is kind of neat, is that I can now reconstruct the pipe diagrams that I had at the start for surface codes, but kind of purely algebraically. So I can start off with my idling kind of logical blocks, and then I can take the mapping cone to introduce this region in the middle, which performs some measurement, and I can reconstruct the kind of classic H-like diagrams and similar kind of pipe diagrams that people use to reason about surface codes. But now it's homology, and so now I can reason about things that are more complicated than this. The main aim of doing this all algebraically, because one could maybe say, all right, but you can just draw it, you could just kind of visualize it. The main aim of doing this algebraically is so that I can use some algebraic tools. So I want to classify what the logical fault equivalence classes are of this kind of big space-time volume that I'm performing all of these surgeries within. And happily, I can use basically the same techniques that I was using right at the start when I was saying about taking the deformed code, where I make some short exact sequence of chain complexes, and then I zoom in to look at the long exact sequence of homologies on this. And so I can organize all of the logical faults in some LDPC code surgery protocol involving many surgeries according to their equivalence classes in terms of homology. So I'm now going to restrict myself to only thinking about doing Z-type logical measurements for pure kind of selfish convenience. And if I have like M of these surgery protocols, which I'm doing successively one after the other, each of these could be measuring many things in parallel, but I'm saying that the logical time steps are, there's M of these. Then when I organize my faults, I have more or less probably what you would expect, which is I have some space-like logical faults in my code blocks, which are just inherited from the codes that I have at each time slice. I have some time-like logical faults which enter into the volume from the bottom and then go out the top again, because I did this hacky thing to make sure that can happen. I then have some time-like logical faults which span the ancilla systems for measurement. So if I go back to this guy here, then I'll have some time-like logical fault which starts here and then goes all the way up here, so that when you take your product of these checks, it will be consistently wrong every single round that you do this. And this is importantly in a different equivalence class to a logical fault which flips the logical which you're measuring, because it's kind of like the difference between having a check error and having a data qubit error which flips a check. Like these are different classes of things. Okay. And then lastly, if I didn't have this kind of exactness property of my my initial A, if you remember, I don't know, 30 minutes ago, then I can introduce kind of new logical faults, which can be very wacky at times. And maybe if I have time, I can talk about them at the end. But basically, the point of this is that this exactness condition, so like gauging all of the cycles, is vital. And all other logical faults that I get are products of these. Okay, so now I'm saying like I have this space-time volume and I'm doing all of these surgeries. And what happens if the idling time between each of these surgeries is reduced to a constant? So I can, again, do this kind of organization. I basically do a case analysis of all of these kind of equivalence classes. And my time-like logical faults are still going to have weight at least d, assuming that this whole space-time volume goes for at least d rounds. The time-like logical faults spanning the ancilla system still have weight d, either because I'm doing them for d rounds or because I'm doing some kind of single-shot surgery with meta-checks, which means that I can get away with having fewer than d rounds while still having only high-weight logical faults. Assuming that I've got this exactness property, then I don't need to worry about those, the funky equivalence classes of logical faults anymore. But the main problem is that if I have some space-like logical faults, which are on different successive rounds of logical measurement, so they live in different deformed codes, then I can take products of these and clean them with space-time stabilizers to make lower weight logical faults. So I've got some little diagram here. So let's say that we've taken our A complexes to not be actually expanding, but just done kind of the minimal possible thing to get the cone code to have distance d. Then the problem is that one can take, so like here I have some initial code. I've got a time slice where I've, sorry, I've got a time slice where I have the cone code of the first surgery, and then I've got the time slice where I've got the cone code of the second surgery. And the problem is that I can have this kind of guy, which starts off as a space-like fault in my top surgery, my top deformed code, and then goes down into my other deformed code. And this is basically because if I had these two, let's say this is a product or is in the same equivalence class as a product of two space-like faults. So if I had some space-like fault here and then I had another space-like fault up top, then when I clean these with by multiplying by space-time stabilizers and introduce some new check errors instead, because these could overlap quite a lot in kind of space-like on qubits in the kind of space-like sense, then if I have, for example, the surface code or something like that, then each of the all of these space-like faults could result in a very low number of checks that are flipped by that. And so if I clean by multiplying by the space-time stabilizers generated by those checks, then I can make a logical fault which is much lower weight than the logical faults which are purely separated into their individual deformed codes. Okay, this is only true if you have this constant number of rounds between. If you have d rounds between all of my surgeries that I'm doing, then it doesn't matter if there's only a very low number of checks in the image of this set of overlapping space-like support, because I'm going to be multiplying that by d anyway, so it doesn't matter. I don't really want to do that, because that's the point of this talk. And so there's basically two ways of fixing this that I know of, and both of them are quite brute force. The first one is to start off with a code which is locally testable, which is very brute force. And the point of this is that if the cleaning issue is that I could have some space-like support which has very little time-like stuff in its image, that can't happen if my initial code is locally testable, because the amount of time-like support must be in some sense proportional to the space-like support. That's actually not quite true, but morally that's what's going on here. And so if I wanted to introduce some new space-time stabilizers here to clean it, then they would clean it onto a large number of time-like errors between the rounds. The second way is to give some conditions on what I'm calling the compacted code. And what the compacted code is I would say it's not the smartest thing in the world. You just take your whole space-time volume and you scrunch it down to be on one plane. What this is saying is that if you take the worst possible case where there are kind of zero time-like errors between these logical rounds, then the only thing that you care about is the space-like distance of this logical fault. And so if you compact everything down, then this is like saying, okay, we make sure that that space-like distance is sufficiently high, and therefore it doesn't matter even if you only add like 2 checks to it to make into this actual logical fault that's happening in my space-time volume. It will still have high weight. Okay, and you might be saying, is this even well-defined? Like, can I take my space-time volume and scrunch it down to one kind of time location? And B, isn't this incredibly hard to compute because you're taking some much bigger code, which probably won't be LDPC, and then trying to compute the distance of that code, which is not going to be fun in general. So for the first part, yes, this is well-defined. And what you can basically think of is if I had all my codes at the start where I was taking mapping cones at different times, this is still well-defined if I just take the sum of all of those chain maps and then make the mapping cone of that. And that's precisely formally what this thing on the right is. Okay, so this is well-defined. The second thing is how easy is it to show that the compacted code has sufficient distance. And essentially, this is, I kind of hinted earlier that there was another problem with doing this kind of ad hoc construction of ancilla systems where they're not actually expanding, but they preserve the code distance. And basically the way of avoiding this problem is having genuine expansion, because you can prove that each mapping cone that you're taking is going to always preserve the code distance kind of no matter what code it's attached to. And so when you do this kind of sum of them, you're going to get a compacted code which has high distance. This is probably not what people want to actually do, and so there are other ways of guaranteeing the distance of the compacted code. Kind of like what we talk about in the rest of the paper is things like full block reading and similar kind of protocols, which are kind of like transversal surgery. And these kinds of protocols always preserve the distance of the compacted code, and so we're in business. Okay, so I hope I've convinced you that cutting down on this idling time is a bit fiddly, but that there are some conditions which you can use to preserve the fault distance. My suspicion is that in practice, people aren't going to actually fulfill those conditions. Instead, what they're more likely to do is just like take a space-time volume, do some Monte Carlo simulation on it, and then if it looks good, then you call it a day. But it's good to know that that you can't do this scrunching the time between LDPC code surgeries for free all of the time. There are some nefarious problems which can occur. The other thing is that like fault complexes are very cool. You can do a lot of stuff with them, and so the kinds of things that I'm kind of thinking about nowadays are like if I have some MBQC protocol, and instead of starting off with a code and then foliating that code and then taking mapping cones on this thing, which is like a bit of a sort of caveman kind of approach. Instead, what if I take I have some general logical protocol that I want to perform, and I make some fault complex for this, which could be very dense, and then I sparsify that whole thing, then can I get an MBQC protocol which is still fault tolerant but uses fewer qubits in time and so on. And there's some nice stuff by Andrew Yuan on mapping cones that are kind of sort of like higher versions of mapping cones, which you can kind of use to think about these kinds of things. So everything I said was about CSS codes, and actually at the end I even specialized even further and only talked about Z measurements, which is like a very restricted class of measurements and codes to begin with. Yeah, there are some kind of ideas of using some kind of symplectic algebra and similar kind of tools to reason about doing this for non-CSS stuff. There's lots of questions in there, like the classic one is like, is there a notion of tensor product which gives me the foliated version of a non-CSS code, which is like, seems like it probably should exist, but also I don't really know how one can go about making it. You can also use fault complexes to reason about circuit distance rather than phenomenological distance if you just like take your circuit and then assign fault locations to all of the places where you can acquire faults. And then lastly, I kind of want to think about looking at MBQC protocols which are non-foliated. So this is kind of similar to the top thing here, but in particular, kind of what I have in mind is if you look at this kind of Naomi Nickerson and Hector Bombin stuff from like 2018, they take some like cluster state and then they look at things which are non-foliated versions of this cluster state in MBQC. And what this is really doing at an algebraic level is it's taking some fault complex, and then this thing here is there's a quasi-isomorphism between them. So it's preserving the equivalence classes of logical faults and the equivalence classes of logical qubits that are kind of maintained through this thing, but the local structure is quite different. And so I'm very curious as to whether we can do this kind of local modification to like start off with some foliated CSS LDPC code, and then tweak it in various ways to try and improve the logical error rate by modifying the local structure such that it's still basically morally the same complex, but better against noise or certain kinds of noise. Yeah. Okay. Thanks. Yeah.
So it seems like once you start iterating the mapping points, you're going to have a lot of different objects in your complex are going to be like the direct sum, or the sum of like many different objects, which actually seems like that's going to lead to a lot of casework.
Mm-hmm.
Do you have any thoughts on like how to do those things?
Yeah, it's quite tough because, well, basically this is kind of a property of the fact that the space-time volumes themselves can be very complicated rather than a problem of like burdensome notation, I would say. And so I'm quite sure that there are cases in which you can simplify things quite dramatically. Like if you're doing what we're calling full block reading, then you can construct your whole kind of space-time volume by taking a tensor product of whatever, if you think about this kind of H-like diagram that I have over here. Oops, that guy. Oop, no, that's wrong. Yeah, okay. Then I could start off by like taking a surface code and then taking a tensor product with some like H-like graph. And that would give me this thing kind of immediately without having to go through blah, blah, blah. I'm making an idling and then I'm taking a mapping cone, yada, yada. But the problem is that basically the kinds of things that we want to do with LDPC codes are a lot more fancy than that. So, yeah. I think that's my answer. Yeah, yeah. Mm-hmm.
You said there were some of these errors that were quite strange.
Mm-hmm.
That you could get. Can you explain a bit more about these?
Yeah. Okay. So I said here that if my ancilla complex is not exact at the 0 degree, then I can get some wacky new logical faults. And the idea is basically that even if I have some, so let's say I'm doing a gauging logical measurement where I have some expander graph, and let's say I leave some of those cycles ungauged, but they happen to also be stabilizers of the original code anyway. Then what I can get is I can get a logical fault, and let's say I have multiple of these in succession. What I can get is a logical fault where it kind of starts off in the ancilla system. It flips some stabilizer checks which are in the original code, which are those cycles are the product of. And then it extends upwards in time from those stabilizer checks through to the next round, and then does a similar thing going back into that ancilla system. Now, as far as I can tell, this doesn't anti-commute with any of the logical operators, and so observables is the word I was looking for. And so this shouldn't on its own be a problem, but the reason why so it's kind of like a gauged logical fault in space-time. But the reason why I asserted immediately afterwards that we always want this exactness property is basically I don't want to have to deal with doing case analysis of dressed logical distance in space-time. Like I'm not doing that. Yeah.
Does anyone else have a question? Let's do it.
You mentioned that it's not proven that the fault distance for a fault complex necessarily translates to the fault distance for an equivalent circuit.
Mm-hmm.
What do you think could go wrong? Is it that the error model on a circuit to the natural LDPC error model?
So in my mind, the translation would be to phenomenological noise anyway. So like you have faults that can happen on data qubits or faults that can happen on checks in the circuit. And so like that kind of mapping between noise models seems fairly clear. The thing that is less clear to me is like if you have a general fault complex, this doesn't need to look anything like a repetition code in time. It doesn't need to have a time-like direction per se. It's just a graph state. And so in order to recover a notion of like circuit fault distance, which you can check is the same as the phenomenological circuit noise distance, you'd have to first be able to always recover a circuit. And it seems kind of likely that, assuming that you assign a time ordering to all of these everything in your graph, every node in your graph state, that you should be able to do this. Like there is some work on extracting circuits from graph states from, I don't know, in the like ZX world and people who deal with kind of space-time modifications. Yeah, basically those things are suitably complicated that it's not clear to me that everything translates perfectly. It seems like vibes-based. It seems like it kind of should, but like. That's gone wrong before.
More questions?
Well, I have like maybe one final question.
Mm-hmm.
We have like a lot of details about various constructions from Isha and then you and like reducing the time of it. But like where are we overall with surgery? Like what's the best procedure to do with value logic? I mean,
Okay, so I suspect that practically what we're actually going to do is basically construct our auxiliary systems more or less ad hoc, but using some heuristics. So as I was saying before, basically the problem with getting good asymptotics for these more fancy kind of parallel schemes is largely because of the difficulty of constructing explicit systolic expanders. But like if your code is a reasonable size and you throw enough compute power at it, then you can construct a bunch of these. And if you're designing an architecture, then you only do this once. Well, okay, maybe you get it wrong, or maybe you decide to change something about your architecture. But like you do this like at the start when you're constructing your architecture, and so you just throw compute power to make this this like auxiliary complex to have all of the things that you want from it. And then you might carve out parts of it, so you might have some like subcomplex or whatever in order to measure specific things. And then you don't bother trying to prove anything about expansion at all, really, at the end of the day. What you do is you just make your auxiliary system and then do Monte Carlo simulation, and then test to see whether it seems to perform well, because like at the end of the day, that's what we care about. So I suspect that a lot of this like nice algebraic stuff probably goes out the window once you start throwing compute at it, which is kind of sad maybe, but.
on that note, let's go to lunch.